Hello everyone, good morning, good afternoon, and welcome to today's webinar, Advancing Process Development with ReactALL, Scalable Reaction Profiling and Modeling. Our presenter today, Trong Nguyen, from Principal Scientist at Pfizer. Before I start, I would like to introduce you Trong. I would like to tell you that the webinar is being recorded and it will be made available to you after this webinar. I think somewhere tomorrow you will receive an email from us with a link to the recording. As usual, if you have watched our webinars before, the webinars are available, the recordings, the videos are available on our website. It will last about 30-45 minutes. If you have questions, please make use of the Q&A section of this platform. Write to us there. And at the end of the webinar, I will read all the questions to Trong, and we'll try to address together all your questions. Also, if after the webinar you still have questions, or you remember you would like to ask something Trong or us Technobis, feel free to write to us at support@reactall.com or via the website. You can also send us your questions. I think this was related to the technical details of the webinar. For those that do not know Technobis, we are a Dutch company located in the north of the Netherlands, a world-leading technology provider for reaction screening, process development, but also solid-state research and formulation. We have two product portfolios, the crystallization systems portfolio, and you see here Crystal Breeder, Crystal 16, and the crystalline instruments in that portfolio. And the more newer, somehow newer portfolio of reaction screening with the ReactALL product. And actually, the webinar today focuses, as also the title of the webinar says it, on the ReactALL and case studies around this. What is ReactALL? ReactALL is a multiple reactor system with automated sampling. Samples are drawn, immediately quenched, diluted, and transferred to the HPLC vial, a standard HPLC vial that then you can take the tray and you put it in your LCMS HPLC. So the beauty of this system is really the automated sampling. Heats, cool, mixes. Mixing is also from the top, no magnetic bars, so no false positives. With 5 needles, so per reactor you have 5 needles independent, so you cannot actually cross-contaminate between one reactor to another one. Maybe we will hear also from our presenter today, but it has been used in the last couple of years, this instrument, for both homogeneous and heterogeneous type of samples reactions. When to think about the ReactALL, maybe in your workflow when you are dealing with reaction screening, optimization, scouting, profile, kinetics. I hear quite a lot lately on reaction kinetics and the use of ReactALL. There are quite a few publications out there. We are quite proud to say that one from 2024, but also 3 publications already this year available in OPRD. And several of them, they are also focusing on kinetics. And with that, I would like to introduce, my computer, sorry for that, to introduce to you our presenter today. Trong is a principal scientist at Pfizer in process chemistry department in Groton, where he drives reaction optimization, kinetic modeling, and scalable process development for late-stage clinical candidates. He earned a PhD at the University of Houston and followed with a postdoctoral fellowship at Indiana University. He's passionate about automation, data-driven predictive modeling, and developing greener solutions in process research and development. Trong, thank you very much for making this webinar today possible. I will make you a presenter now, and you should be able to share your slides.
Can you see my slide now?
Wait, just 1 second. I do not see. You need to try to share again. Right?
Nice. So okay. So back to my.
Yes.
Oh, no, sorry.
It's coming. Yes, and you need to put it in presentation mode now. Yes, perfect.
So everything's
yes.
now.
Yes, perfect. Thank you very much, Trong. I will be in the background. I will mute myself.
Okay. Well, you know, first of all, thanks for your invitation and really nice introduction. Good afternoon, good morning, everyone. So, you know, we may heard a lot about the ReactALL, but the goal today, I basically try to convince you that, you know, what's the ReactALL, what we can do with it, and how it can accelerate the process development workflow. So, you know, you already just heard from Carmen that, you know, the biggest thing about the ReactALL is it can generate representative kinetic data. But you know, at first, why we even need kinetic data especially in process development? For example, if you have a reaction that you need to do optimization, and then you have 5 different reaction conditions, and then you run reaction, and then you generate the endpoint of your reaction condition. For example, in this case, so many of us probably choose the condition which generate the highest conversion. For example, in this case, the condition D. But what if this is the reality? So many scenario could happen in between. If we don't have kinetic data, your reaction could be, you know, fast and then stall like A. It could be a nice kinetic curve like B, but it also could, you know, super fast from the beginning and then decompose like C. It could be also, you know, slow at the beginning and then fast later, like an S shape, or the bell shape, like in case of E. So what I want to point out is without interval data, we don't know what actually happened during the entire course of the reactions. You know, and with the kinetic data, you know, we can do a lot of stuff in process development, but I want to highlight 2 key applications. The first one is optimization. We will understand the reaction behavior much better with kinetic data, and at the same time we have a better impurity control strategy. And you know, by the end, it can generate decision making data, so we will know what we can do to further optimize, or what reaction we can use or compare between reaction conditions. The second one is the higher level is predictive modeling. So the kinetic data is very useful when we want to, you know, when you have a good kinetic model is, you know, and you actually can significantly reduce the experimentation later on, you know, and a lot of time, you know, it actually can significantly accelerate the workflow and even the regulatory filings at the late stage process development. And of course, it's can have higher level for scale up in process chemistry. To do all of this, we need kinetic data, and we need to know how to do sampling. What I mean is representative, reliable sampling, not just normal sampling. Why we need to do reliable sampling? Because physical property is really challenging issue in reaction condition. You could have very poor physical properties. Your reaction could be thick slurry, it could be viscous with solid, it could be a multi-phases reaction, or it could be just ugly. So because the challenge of the physical property, a lot of time the sampling is not representative and the result may not reliable. One of the most common probably ways, probably manual sampling. So basically we just go to the lab and use a pipette and take the sample. The problem with this approach is, you can have different data from different chemists in one reaction. And it's also very laborious. None of us can stay overnight or do like that to just generate kinetic data. A second option is easy sampler. This probably is the most common technique or equipment in the industry setting. Yeah, it's definitely can get consistent data, but the challenge from easy sampler is throughputs. And a lot of time we need decent scale, the reaction scale, to enable the sampling, like in the Easy Max 50 mil, which also require good amounts of material. We also have something like Amigo Cam. This platform provide better high throughput experimentation. You have reaction incorporate in the sampling. So, and then, but the problem with that is it tends to be a higher cost and also not very scale predictive, mainly because it's used the star, which is not representative as the overhead stirrer. And at the high end of these technologies is we have some commercial available platform that be able to automate the dosing liquid solid reaction in the atmosphere, like the chem speed. But when we go to higher level of automations and advancements, we often come with higher costs, larger footprint, and a lot of time increase the complexity. So, because all of this, we want to have a middle point, a platform that can generate automated sampling at a medium throughput level, but it's also not complicated and too much expensive. Because of that, the reactors was developed. Is a initially, is a co-developed between Technovus and some pharmaceutical companies. One of that is Pfizer. So Carmen's already talked about that, but I want to highlight for some people who haven't heard about that in details. So it's basically five independent reactor that's heat cooled independently, which it be able to quench, dilute, and then rinse, and then the sample will be in the tray, and you just wrap the tray to SPLC analysis. The key about this is what we call smart cap. So it's how a helical stirrer in a vial scale. So it basically mimic overhead stirrers to avoid grinding, attrition. So it's how a very good mimic, with some like other overhead stirrer compared to the reaction that people run in vial, they run in the stir bar. Basically behind that is the mechanism where the reactor can allow the smart cap to pressurize so that the liquid, the reaction mixture will go to the top, and then we close the valve, and then we have the quench the dilute pass by to get your sample, and then we continue the reactions. You can see in the amidations. And it's super useful when it has been proved that it actually can tackle a lot of challenging physical properties. So we so far happy about that. Another tool is we call the dosing unit. It can independently dose in different speed and volume in different reactor. It's also incorporated with the software. Speaking of the software, it's how a very user-friendly interface. So basically, you just drag the function and then build your own program. If you want to heat it up, you just drag heat it up and then dose and then sample and then rinse. So it's very user-friendly, easy to use. And also we do process development. We care more about TR, especially in scale up, because the reactor in the vial are very small. And if we put a thermocouple, it's probably very packed. So we have Technobase have a very nice technology to get the TR control without a thermocouple, just using IR technologies, which is really nice. And for those do a lot with crystallization, it actually have a camera in front of each of the reactor that actually can capture your reaction physical property and even like a particle size by time. You can see, you actually can see the physical property change by time. And I think it's super useful, especially in crystallizations. So, now we know what's the react on, what's its functions, and then what it can do. So personally, I think it's just up to our imagination. But at Pfizer, file is super useful for some certain workflow. For example, if you have certain hit from the high field screening, you just validate in the React on instead of go to EasyMac, maybe 50 mil volume, which is a lot of material. You can also do some kinds of MIDI DOEs or all fast or even late state DOE. It actually have a very generate how a very comparable result. You can also do route scouting, but again, the biggest advantage of this one, it can generate reliable kinetic data. That's for you to do modeling to speed up the process development. Like before React on, we usually have a constraint in terms of material, especially in the early stage, and sometimes cost. And to generate the data, it costs like two weeks to actually can have a good set of data. But after React on, we significantly save the time and materials, and the whole data generation workflow probably takes about 2-3 days. So it's a huge improvement, at least for us. So with that, now we know it's reliable to use and what it can be used. I will show you 3 different cases that so basically show you it actually can generate reliable comparable data compared to other platform, and we can do certain useful thing with the data. So the first one is as it catalyze or promotes the bug protection, and then stylization to generate a key intermediate in the clinical candidate. And this reaction, it actually have observable, 2 intermediate and generate 2 impurities. So generally, this is complicated multi-mechanistic reactions. Speaking of the physical properties, we have inconsistent data, mainly when we do manual sampling just by a pipette, mainly because the poor physical property. So because of that, we don't have reliable, high quality data to do, subsequent analysis, for example, DOEs. So we think, okay, it's probably a good case to test the React on. So and then we did. So, earlier what we did is we run a reaction in 100 mil scale in platform, we call six stack or FlexCube. So it's basically a smaller version of the reactor. It have very good mixing and temperature control. But the downside of that is doesn't have automation of assembling, so we have to do manually. And obviously, at the first glance, you see that we have a huge data gap in between. Basically, nobody can stay overnight to take a sample here, so you don't know what happened in between, and it's how inconsistent result. And another thing is because the large scale, so we basically have to use roughly 5 RAM to actually can run the reactions. And then we, replicate a reaction in ReactALL in 5 mil scale. Is overall you can see that it can capture very well the entire course of the reaction. So now we know that nothing really happened in between. And then in general, you can see that it's how a strong agreement across multiple components, the impurity and the intermediates. And it has, even with poor physical property like a thick slurry like this, it actually have a good comparable data between the two reaction platform. And another highlight is we only use about 6% of the material, so it's actually a big benefit, especially in the early stage. But this is only one reaction. It may not strong enough to convince you that okay, this is good for this. The react only good for this reaction. So we go further by we replicate the entire DOEs, which is 20 reactions. So we run another 19 reaction. These you can see the very sensitive data. So in general, it's have a very good alignment and good kinetic data capture. But to compare the entire data set across 20 reaction with using certain statistical model to align them to see whether we have a good alignment between them. So this is the parity plot, basically the alignment between the data set from the FlexCube and from the ReactALL. First of all, if you take a look on the product and starting material, it actually have very good alignment. So, and basically this is exactly what we need. So we is about that. If you take a look on the impurity and the intermediate, yes, it's how a lower level of agreement, but presumably because it's first of all it has low level across reaction. Secondly, we have some challenge of the stability of the sample, so it's actually quite unstable. So that explains. But overall, across the set of the reaction, we have a good alignment between the ReactALL and FlexCube. So all of this, I just want to show you that even poor physical property, it can generate decent, reliable data. Second case is basically now we can confident to yield the ReactALL, but and then what we can do with that. So we can do many things with that. So one example here is we run amidation reaction for generate intermediate. This is the amidation reaction promoted by EDCA HOPO in acetonitrile and water. So the issue of this reaction is generate notorious acid urea byproduct, typically from EDCI. So and it cannot occur in crystallization. So we must control or minimize the impurities. Another challenge for this specific project is at that time we have very limited amounts of starting materials, and the timeline is very fast. So, the questions at that time is how we can quickly optimize the reaction, in another word, maximize the product and minimize the impurity with the minimal amount of materials. So, we can approach by many ways, but what we did is, typical workflow is, this is what we think we can do, that leverage the kinetic data from ReactALL to, quickly solve a challenge, something like this. So first, we can identify what is the impactful variable need to study, and then we decide what is the optimal conditions, and then we run these conditions in the ReactALL, and then we can use certain available data-driven model to fit the data, and then with a good model we can use that to interpolate or how a good space design or inform what reaction to do next, and finally validate the result. So this is a typical workload. We think it would be good in case you need to get a rapid reaction optimization using the React. So with that, so we figured that we have four main variables, the amine Hopewell EDCI equivalence and the Solomon ratio, that will generate us 5 the optimal conditions, and then we run in the ReactALL, and then we fit the data using certain tool. So in this case, we use reaction profiler, which is available in DynaChem. It's actually a very nice and easy tool to use. But you can use any tool available to generate a fit model. So by this way, we can map out the key driving force in a very with a small effort. So after that, we have the kinetic data, and then we fit all the data in the reaction profiler. Happily, we have a very good fit across the products, starting material, and the byproduct. So we kind of, potentially confident or to use or to tell us what to do next. So, one of the way to do that is we generate a control plot with the constraint of the Hubble and EDCI equivalents. So you can see here, the model or the tool actually can provide a very clear response surface control plot for reaction optimizations. So if we want to get the high yield, or this corner, you can see here, we want to get the highest the amount of Hubble or less the amount of EDCI. And similarly, if we want to minimize the amounts of impurity, you also want to highest the amount of Hubble and less amounts of EDCI. So, just by nice reaction, we can quickly know that. But to target the goal, we just need to lower the amount of DCI and higher the amount of Hubble. This is just one example to show what we can do with it. And more importantly, we know that just by with 5 grams of the material, and basically from planning exclude the reaction time for planning is, and then data processing will probably only cost about less than a day. We can figure out what to do next for the next day. Moving forward, another case study where we how a kinetic model or mechanistic model of SNAR reaction to basically to synthesis this intermediate. So speaking of the reaction, is a very long reaction, but another challenge is is solidified when the reaction upon the reaction completion. The reason for that is because when the product form, it actually have a lower solubility in IPA. That's why, you know, the moist form it start to precipitate out, especially at room temperature. So first of all, it's probably the ultimate test for the reactor. So we really want to see whether it can handle such poor physical properties. From the process development standpoint, the main goal here, how we can optimize the condition, specifically how we can lower the time. You know, because I'm not a kinetic modeler or any, I'm not expert by any means, but because I mentioned about the kinetic, the data-driven model, so it's probably worth to compare the pros and cons between a mechanistic model and empirical models. So this is what I think. You know, you can use empirical model or kinds of hybrid. You leverage the kinetic curves and then use certain statistical model to capture the reaction. This approach here, data driven, is usually fast, easy to use, but because we completely ignore the mechanism, so it's how basically a limited level of extrapolation. On the other hand, mechanistic model based on the first principle, and it will based on the mechanistic understanding. So it's how a better level extrapolation to the process. But the downside of that is often require more data, more efforts, and a lot of time we have to test multiple mechanisms to get a good fit. But you know, these approaches actually complement each other. It depends on your stage and what you need at that time. You know, by the end of the day, we don't have a perfect model, but if we can have a useful model to improve the process development, that's all we need. With that, we need to answer the first question, whether the reactor can handle these such poor physical properties. To do that, we basically also have previous data in positive, and we select 5 reaction condition, you know, different temperature, reaction concentration, and then we repeat the same reaction condition in reactor. So overall, you can see that we actually have good capture, but across 5 experiments, we also have a quite good alignment between the reactor from the data from the reactor and the previous data, even, you know, in a very concentrated reaction. So we, you know, happy about that, and we think, you know, basically reactor it can generate, you know, reliable data even for this reaction. So with that, we move forward to yield reaction for the kinetic model with development. So, and then we went back, and then we think we try to, you know, for the purpose of this talk, we try to make a simple model if possible. So we basically design 5 different experiments. The main goal is try to capture the temperature and the concentration of the reaction. So you can see that, you know, this is the kinetic curves of the 5 experiments. So expected, you know, when you get higher temperature, you get faster reaction. But when you change all the parameters like the amount of space or the concentration, it's really not really, you know, change or impact the reaction rates. So, you know, with that, we fit in the model using, you know, modify Arrhenius type equations with the the rate constant at the reference temperature. We have to fit in. We have a very good fit with low standard deviation, and the reaction appeared to be a second order. It's very typical for SNAR reactions. So you can also see in the model fit across the trained data. So it have very good fit basically across 5 experiments. So suggests that we may have a good model to do reaction optimization or predict the scenario of the reaction conditions. But first of all, we need to validate the model. So we try to simulate 4 different conditions, the temperature, the amount of space, the concentration, and then when we validate that in the reactor, again using to compare between the simulation data and experimental data. So overall, it's a good fit across 5 experiments. It's it's even outside the range of the design temperature, like 40 degrees and 95 degrees. I think it's useful to discuss this result in terms of practical benefits, because at the time 4 or 5 years ago, we think that this reaction will speed up if we run at higher temperature. So to prove that, because we don't have the model or anything at the time, obviously ReactALL not exist at the time too. So we try to set up a very complicated reaction setup, to run the reaction at the superheat condition to prove the hypothesis. But then ultimately later on, we just found that it's not actually improve the reaction. But if you have the model derived from kinetic data, you actually can quickly answer that question instead of take a lot of effort to go to the lab and run the experiment. For the base, you can, when we lower the amount of base, it doesn't change much the reaction rate, suggests that the amount of base have a minimal impact to the reaction rate. And then for higher concentration, actually the reaction actually speed up. But eventually, we didn't pursue this condition, mainly because it worsened significantly the physical property, so it's impossible to scale. In the late stage, we also typically generate control plot to know the operational space or window. So in this case, it also can do the same thing, where the red regions is where the product over 90% of the conversion. So we can do other stuff, but I want to highlight these things that we depends on our ability. We can provide many useful information for process development. And lastly, for this result, I want to highlight again, it actually yields a tiny fraction of a material compared to previous study, probably only about 3%. So that is significantly improvement in material saving. With that, basically by the end of my talk, so I try to share what we trying to develop here. So we talk a lot about the reactor, but that basically the center of broader pictures, where we want to be more productive, where we think that if we have a preparation desk, with a robot that handle on the liquid solid dosing, and then pick the reaction to the reactor, and then run in LC or direct LC, and using available AI ML Bayesian optimization to suggest the next experiment, and then keep looping until we have a satisfied result. So that's the ultimate goal. We're not there yet, but that's what we try to develop. And with that, I'm thankful for all of the colleagues from Pfizer and the technology team, and happy to answer any questions.
Thank you very much, Ron. Really appreciate all the case studies, and it was good to see also a bit more complicated case studies. I do still remember this photo of you. I think it was case study number 3 with reactor the other way around, and then everything blocked there. So it looked like, in a few words, that it looked simple, but I think it was a lot of work behind it. I think it was not that straightforward, but I'm happy to see that still some success. Can you say anything about that case? A bit, some additional. How long time did it really took to? Because yeah, it's still that reactor the other way around and everything blocked there. It's quite a challenge. Let's say. Let's call it in a very nice way.
Yes, just to be clear, so that's the after reaction where the reaction temperature go back into like a 23 degree room temperature.
Yeah.
So that's where it's precipitate completely, But at the reaction temperature, we say, 80 or something, it actually slurry.
Yeah.
It keep a slurry because it heat it up. So the important here to point out is because that suggests that even when it moved up in the smart cap, it didn't precipitate because on the top of the smart cap, assuming that the temperature is actually dropped, but it didn't precipitate. So that's the thing to highlight because, but again, if you put the reaction out, yeah, it's completely precipitate.
Yeah. So temperature control is quite important, indeed. And somebody had a question related to the temperature range of the reactor. Maybe we can address that one already because we are talking about temperature. I think the lowest is -25 degrees and the highest 150 degrees. Okay, I will try to read a few of the questions that we have received. One of them, it's saying, you mentioned about reaction kinetics, and the person that wrote thinks that maybe he missed a bit, didn't understand exactly what the reactor, if the reactor monitors reaction progress with itself or submit those samples to HPLC. Well, you still need the HPLC, right?
Yeah, so it just automated sampling platform to get the data. We still need to do LC to analyze that.
Yes. And he also asks, it comes with product impurity mass detection. No, the reactor not. But I think there are other methods on how to do that, right? Offline.
Sorry, what was the questions?
If the reactor comes with product or impurity mass detection.
We don't have mass detection. That's probably basically is analytic or analysis would completely separate from the reactor.
Yes, LCMS or so, right? Yes. The temperature. Oh, another question. What about when using heterogeneous reactions? Example, with solid inorganic reagents, does the sampling line block?
The short answer is depends on your reaction. We haven't tested, different types of heterogeneous reaction, cross-coupling reaction. 90% is handled very well.
And I think the lines are not that big of a problem. Because what we are always saying, and what I remember from the development of the design the time of this reactor is that from the cap, so from the moment you took the sample until the needles, you do not have valves, so it should in principle, in that place should go smooth. But okay, I don't want to say that we have a magic ball and everything goes smooth. We are all scientists, chemists working in the lab, and the reality is that sometimes we also have challenges, right? I have another one, just 1 second. For reaction, they remain as slurries at the Rx and temperature, so in inorganic suspensions. Have you encountered limiting cases in which this was an issue with representative of consistent sampling? So the question is about how consistent is the sampling.
So usually, you know, when we test we pick the same reaction and at the same time, and then we pick basically 5 times, and then we just get the absolute area of those sample, and then if they are relatively similar, so we consider it's consistent.
So the same person or somebody else is asking how is the sample line cleaned in between sampling? So with these rings, we call them steps, that your rinse goes through the lines, but also nitrogen is purged through the lines also to dry, because you don't want to have your rinse solvent in your next sample or so.
Okay, so one important thing to highlight here is we try to avoid cross contamination. It has been doing a very good job in terms of avoiding cross contamination. Speaking about cleaning, the line is how, you know, if you use some kind of volatile solvent, it usually better. It's like acetonitrile. So, you know, when it dry out, it will dry out quickly, but it also can clean the smart cap too. So you can do manual cleaning, but you know, it's the machine Excel can also do that.
Yes, indeed, automatically, and so yeah. One more question, Trong, and then we try to finish. Do you feel that the small scale allows for meaningful workup and physical yield determination?
Probably meaningful in terms of generated kinetic data. So if because, you know, if you're looking for something like isolation, yeah, this is probably, and you're looking for a larger material of the of your products, probably not that's what you interest. But is in terms of generated data is how, because, you know, if you have the representative data, it will be the same if either you run in the ReactALL or the EasyMac, right? So if we can sell the material, why not use something that we use less materials?
Indeed. And then the camera, somebody has a question about the camera. If inside of the reactor vial, well, the camera is not inside of the reactor, but it's outside. All our analytics at Technobiz we have through the vial. We try to, as much as possible, if you can measure particle and crystal size. I think most of the instruments that we have now on the market, they have these cameras that allows you to see more of the reactor, a bigger part of the reactor. So is more from a qualitative point of view to see, okay, do I have oiling out, precipitation, or from this point of view, more information. Although we do have, we have done already tests with different magnification cameras using the technology that we have on our crystalline, so on an instrument from the crystallization systems, where in principle you could also determine particle size with the ReactALL. I don't know if any of your ReactALLs have different magnification cameras, or is just one. I'm not very sure.
I think in Listen Visor we have one unit that ties the camera I think it's not something like we fully apply into a workflow, but yeah, we try to develop using a camera to do more than just looking for physical properties.
Yeah. Do you recall the vial, the volume of the reactor? Now I don't have this information, Trong.
Fully is 16 mil. Yeah, so the operational volume probably 5 mil. That will give you in basically, at least you need to, the level need to be higher than the
sampling tube.
So,
yes,
so
a minimum of 5. Yeah. And somebody is asking about the price of the ReactALL. Unfortunately, we are, or fortunately, I don't know how to call it, we are chemists. I'm also a scientist. I'm not a salesperson, so I will not be able to help. But if you would like to know more, please contact us via the email, and one of my sales colleagues can get in contact with you. I think we stop here. We are already going towards the hour. Once again, thank you very much, Ron. Really insightful, a lot of case studies, and case studies also really problematic, and so that also showing a bit how you can also go use less material, but meaningful for larger scale. Quite diverse. Thank you very much. I really appreciate taking you the time and also to make this presentation, to share the data with our attendees today, and being here today. We will be back after the, we have Stegnobi's one more webinar, but it's on crystallization systems soon. After the summer, we start a series of 3 or 4 webinars with on reaction screening on with Eli Lilly. They have a few publications, and we will try after the summer to focus again on those webinars. Until then, there are quite a few publications out there, articles, so quite some materials to read. Thank you once again, Trong. Thank you all for attending today. You will receive a link to this recording tomorrow from my colleagues from marketing. Thank you.
Bye-bye.